I got really worried on Saturday after the game in the round of 16. I was still confused about this Friday versus Thursday thing, but luckily the Colombian game is at 3 o'clock tomorrow. So I want to tell you about some joint work with Vic Reiner and Dennis Stanton, who are also both at the University of Minnesota. And so the problem I want to tell you about is actually a problem in the general linear group over finite field, but let me motivate it with some really nice combinatorics having to do with the symmetric group. So take the long cycle. The cycle that sends 1 to 2 and 2 to 3, and so on, and then sends n back to 1. And I want to think about writing it as a product of transpositions. So first thing I want to emphasize, not simple transpositions. I'm not talking about reduced words. I'm talking about any transpositions. And so if you want to write the long cycle as a product of transpositions, okay, you need at least n minus 1 of them, or you can't do this. And then it's a theorem. So there's this paper of Hurwitz from the 1890s, and I'm pretty sure it doesn't actually contain this theorem, but it was clear, like, he could have written down this theorem if he wanted to. The number of factorizations of the long cycle as a product of n minus 1 transpositions is n to the n minus 2. And so I want to show you a proof of this, not Hurwitz's proof, but a proof by Dinesh from the 1950s. It's a really, really pretty proof. So here's how it goes. Okay, n to the n minus 2. So I'm going to show you a tree in a minute, right? So what I want to do is, it's not quite a bijection. So I want to take trees on n vertices, and then I also want to order their edges. All right, so, well, there are n to the n minus 2 trees, and then for each tree it has n minus 1 edges, so there are n minus 1 factorial times n to the n minus 2 ways to do this. And then if you give me an edge labeled tree like this, what I'm going to do is I'm going to take each edge in the order that they're listed, and I'm going to turn it into a transposition, right? So you give me a tree, it has an edge AB, so I'm going to turn that into the transposition AB. And I keep track of the order, and then I just multiply them in that order. So I'll show a picture on the next slide. So for every tree, you get a factorization like this, and it turns out that you get every factorization of every n cycle this way. And of course, there are n minus 1 factorial n cycles, so you get to cancel the n minus 1 factorials, and you're done. So here's a picture of that. Here's a tree on 6 vertices. Its 5 edges are labeled, so the first edge is connecting the vertices 4 and 6 there, so I write down the transposition 4, 6, and so on, and you multiply these transpositions, and you get a nice 6 cycle, just like you should. And it's, okay, so I maybe skipped the why this works part of the proof, but that's actually, you know, something that you can work out for yourself in 5 or 10 minutes if you think about it. So okay, so this is a very pretty solution to this question. So let me talk about some generalizations of this question that you could ask about. So okay, you could seek to factor other elements or use other factors. So I think we saw a little bit of this in Guillaume Chapuis's talk the other day. There's a really big industry here. I didn't try to write down names because, you know, it's just a really, really long list over a long period of time. So there's a huge amount of interest in that. There's also a sort of Coxeter group version of this story. I'll say a tiny bit more about it at the end, but you get some version of non-crossing partition combinatorics associated to every file group, say, or maybe even every complex reflection group, and you get Catalan combinatorics, and it's nice stuff. Or, okay, less ambitiously, you could just say, I only showed you what goes on when you have exactly n minus 1 transpositions. What if you let me have more transpositions? And so this is something that David Jackson dealt with in the 80s. And so, all right, so now I'm going to take n and l positive integers and factor an n cycle as a product of L transpositions. And this is what you get. So let me talk about this formula for a minute. It's ugly, right? So it's not positive. I mean, you've got a sign here but you also get signs here when k is big, right? So it's definitely not positive. It's not integral, actually, right? You're dividing by n factorial, but also this can be a half integer. So for if n is one of even and odd, all of these summands have 2's in the denominator. It's not obvious that when L is less than n minus 1, this gives 0. It's not obvious when L is equal to n minus 1 that you get n to the n minus 2. Okay, so it's almost obvious that the parity condition works okay, right? Like you need L and n minus 1 to have the same parity for the answer to be non-zero. And if you check, like there you actually have 2 summands cancel pairwise. So that's like, only takes a little bit of thinking. So this is kind of horrible. Okay, it can be rewritten in different ways. There are positive versions of this formula, although they're not like really nice or anything, but they exist. I kind of like the generating function because at least there you can see n to the n minus 2 and you can see n minus 1 showing up. And it factors, which is maybe a little surprising. So you can solve this kind of question in a great deal more generality. For example, Shafir-Stokes' paper from a couple years ago has the sort of analogous thing for complex reflection groups. So this is not really, somehow it's not really combinatorial, and so I'll say some more about where this actually comes from later, but let me now tell you about, okay, so this is symmetric group motivation. Now let me tell you about the question that actually we solved. So what I want to do is I want to take the questions that we were just talking about, and I want to translate them from the symmetric group to the general linear group over a finite field. And so, okay, to convince you that I'm going to be talking about an analogous question, I should tell you what the analogies for a long cycle and a transposition are. So we're going to say that the thing analogous to a long cycle is something called a Singer cycle, and the thing analogous to a transposition is something called a reflection. And then, okay, so I have to convince you that those are good choices. And then once you believe that those are good choices, you are obligated to believe that the right question is, how many factorizations are there of a Singer cycle as a product of reflections? So let me tell you what a Singer cycle is. All right, this took me a while to wrap my brain around the first time. So first, f q to the n. So this is a field with q to the n elements. It's a vector space over fq of dimension n. Okay, there's not really a canonical way to view it like that, so choose an isomorphism that you happen to like. And now, okay, so now multiplication in the bigger field is actually fq linear. If you write down what that means, it's basically some special commutation and distributivity property in the field translates exactly to being linear as a multiplication in the vector space. So you pick up automatically, once you choose this isomorphism, an injection of fq to the n cross into invertible n by n matrices over fq. All right, I promise. And so then C, so the thing that I want to call a long cycle is going to be, okay, so well, fq to the n cross, that's the multiplicative group of a finite field, so it's a cyclic group, so it has a cyclic generator, and so C is going to be one of those images. So, okay, so there are lots of these things, right? For every isomorphism and for every cyclic generator, you get one of these things, and if that's not closed under conjugacy, then you can take their conjugates also. Probably is closed under conjugacy, though. Okay, so that's a Singer cycle. And so at this point, you have no reason at all, if you haven't seen these things before, to believe that these are really analogous to the long cycle in Sn. So let me try and intimidate you into believing that. The long cycle, when you act on say, subsets of 1 to n, it does not stabilize any of them. It doesn't, except, okay, stupidly, the empty set and the whole set. And so the Singer cycle doesn't have any non-trivial stable space, okay? And similarly, the long cycle acts transitively on your basic points 1 to n, and the Singer cycle is acting transitively on the one-dimensional subspaces. And, okay, I'm at the University of Minnesota, so the long cycle has a cyclic sieving phenomenon when you act on k subsets using some q binomial coefficient, and so the Singer cycle has a cyclic sieving phenomenon, but when it acts on k-dimensional subspaces, and it uses a qt binomial coefficient, and I should say that this is definitely not the same as the Hagelin-Garcia style qt binomial coefficient. This is not a polynomial in q, actually. It's a polynomial in t when q is fixed, but the q's are in the exponents. It's a really, really different sort of object. Okay, and maybe we'll see a couple more sort of analogous features. It would please me greatly that if this isn't convincing you, pretend that it's convincing for the remaining 13 minutes or so of the talk. Okay, so that's a Singer cycle. I have to tell you what reflections are. So okay, so reflections, that's pretty easy. If you think of the symmetric group as permutation matrices, then the transpositions are precisely the reflections, orthogonal reflections. As matrices, they fix at n-1 dimensional hyperplane. And so I'm gonna, okay, well, we don't have orthogonality over FQ, but so I'll just call the reflections the things that pointwise fix a hyperplane. One sort of funny difference is that in SN, all the transpositions are conjugate to each other, and in GLNFQ, this is not true. You have a bunch of them with non-1 eigenvalues, and so those are all diagonalizable. So they all are similar to one of these. And then you also have a bunch of them who have determinant 1, and those are all similar to this matrix with all eigenvalues 1 and a single Jordan block of size 2. So you actually have Q minus 1 conjugacy classes of reflections in GLN, and I sort of really want to think of them just as sort of two different flavors, the semi-simple reflections and the transvections.
Your reflections don't have to be involutory?
That's correct. Okay. They do not have to be involutions. Generally, they are not involutions. So, yeah, if you like, this is sort of in the flavor of, say, a complex reflection group where reflections can have higher order. Okay, so that's what a long cycle is, sorry, a Singer cycle, and that's what a reflection is. So now our question is, how many ways are there to factor a long cycle as a product of reflections? And so first we've got our sort of Q version of the Dinesh result. So the number of shortest factorizations, which happens to be into n reflections of a Singer cycle, is really pretty numbered, Q to the n minus 1 to the n minus 1. So let's compare that with Dinesh's answer, 2 n to the n minus 2. And, okay, and so we also have the sort of Jackson type results. You allow longer factorizations, and what you get, I mean, actually, to be honest, this is maybe like slightly less ugly even. I mean, at least it has the virtue of kind of obviously being a polynomial in Q, which is better than not something that wasn't obviously an integer. I mean, we had to massage it a little bit to get this. There are many, many, many ways you can write this. This, I think, is the most attractive one. Still, definitely not a positive formula, though. And here I've got a Q binomial coefficient in there. And we can actually do more than this. We can refine, if you wanted to specify the conjugacy classes of reflections that I'm allowed to use for each reflection. I can tell you what the answer is there. Okay, so these are our theorems. I want to tell you a little bit about how we proved our theorems. First, I want to tell you how we didn't prove our theorems. So I'm not going to show you a really pretty argument involving a Q analog of trees, because we don't have one. If you can come up with one, that would make me really happy. That last formula, I'm going to go back for a second. This formula, okay, I mean, look at this, right? This is obviously from inclusion, exclusion, right? I mean, it's got a, you know, I mean, and even if it's not obviously from inclusion, exclusion, then it's from like some Q version of inclusion. I mean, it's just totally clear, right? Okay, so I have no idea how to do that. It would be great if there were a sort of combinatorial way to come up with that formula. I'm standing here talking about Q analogs, and I haven't said anything about the limit as Q goes to 1. And here it is, and like, I mean, okay, so, you know, all right, pretend this isn't here for a second. Like, that's a kind of nice number. I have no a priori explanation for why this should be what you get when you take Q goes to 1. I don't have any idea what that means in the symmetric group. It's certainly not Jackson's formula. I don't know. All right, so these are a bunch of things that I can't explain. Now let me tell you actually how we did what we did. And so it turns out this is a really old idea. It goes back to Frobenius, and this is a great lemma. It works, as you can see, for any finite group. You can answer questions of this sort, at least provided you can write down the things that appear in the formula, right? So you take any finite group, you take any unions of conjugacy classes, so those are like reflections or maybe transvections or reflections with a particular determinant or a particular subset of determinants or something, and any element of your group. And so Frobenius tells you how to answer the analogous question. How do you factor your element of your group as a product where each factor comes from these selected union of conjugacy classes? And it's just this sum. Okay, just this sum, which involves a sum over the irreducible representations of your group of products of degrees of the representations, character values at the element you're factoring, some character values at these sort of sums over these conjugacy classes in the group algebra. This is actually not a terribly hard result to prove. It's sort of a clever coefficient extraction in the group algebra. Like if you were to expand out the product Z1 through ZL, the coefficient of C is the answer to the question. And so then everything else in this formula is extracting that coefficient using the fact that the group algebra carries the regular representation. And this is exactly how Jackson got his formula, and this is how, for example, Chapuis and Stumpf do it in the case of the complex reflection groups. Okay, so if you wanted to do what Jackson did and do this for Sn, what would you need? So you need the irreducible representations, you need their degrees, you need their character values on a long cycle, and you need their character values on transpositions. And so like, okay, irreducible representations are partitions, degrees are hook-length formulas, character values on long cycles are really nice because they're usually 0, right? Murnaghan Nakayama tells you your shape had better be a hook. And okay, character values on transpositions are not like something I know off the top of my head, but like with a little bit of elbow grease, you can work it out. So that's great. So in our case, all right, well, you need all the same stuff. So the irreducible representations are, well, okay, so I mean, we didn't like invent the character theory of GLNF2, right? So the paper of Green in 1955 really worked out most of the representation theory that we need. So he wrote down irreducible representations. Their degrees are a cube hook formula. Okay, this paper of Silberg and Zink gives you enough information to sort of play around with these character values of the Singer cycle. In particular, again, you have something, there's whatever this is, it's more complicated. Whatever it is, there are partitions involved, and this is 0 unless that partition is a hook shape. So that's kind of nice. And then you've got character values on reflections, and so I guess Hildebrand did the transvections, and then, okay, you can get the semi-simples with a little bit of elbow grease. So it's a very similar story. Every part of it is worse than the symmetric group part, but we're able to cobble together sort of just enough explicit values to handle this. Let me show you sort of an example of the kind of theorem that we were using. So here's, okay, so that the relevant character values are lambda is a partition. And okay, so this is the theorem that's telling you what these character values are on semi-simple reflections, right? And so, okay, and so you have this nice, like, it's usually 0. Okay, that's really helpful. And then, okay, except for certain u, but they're kind of almost degenerate case, and at least an easy to understand case, right? It's just for GL1 that the u can come. All right, and in that case, there's this nice looking combinatorial formula for what the character value is, and in particular, we only need it for hooks, and in that case, it looks even simpler. It's just, you know, u is a one-dimensional character, so you just evaluate on the determinant, and you pick up the power of q. So we get a whole bunch of results like this, and then we just throw them all into the Genius's formula, and we compute. And so in some sense, you can do any problem you want like this. Of course, in practice, you know, getting these character values can be really hard. So that's our proof. I do want to spend 1 or 2 minutes talking about an open problem. So in the symmetric group case, if you look at these shortest factorizations of the long cycle, and you look at all of the permutations that you pass through, so you're taking a factorization and you look at the partial products of this factorization until you get to the cycle, and then you look at that for all factorizations. So this is some collection of permutations, and it has a natural coset structure with the identity at the bottom and the long cycle at the top, and then at the first level are all the transpositions that you can use, and then so on. And so it turns out that this is the same as the lattice of non-crossing partitions, which is pretty nice. And so this gives you a way of, so this is what I mentioned way back at the beginning, that, you know, okay, so for a general reflection group, you get an analog of the lattice of non-crossing partitions by taking these sort of partial products as the definition of your lattice. And then you can get a sort of Catalan type combinatorics for any W. So we could ask about trying to do the same thing here. All right, so you take your Singer cycle on top, you take your identity on the bottom, and then you take all of the matrices that you pass through while you're factoring in. And it has some nice features that are reminiscent of features of the lattice of non-crossing partitions. Like so if you want to know where somebody is, what rank they're at in this poset, it's just codimension of fixed space. So that's nifty. And if you send one of these matrices to its fixed space, or you send all of these matrices to their fixed space, that's an order and rank preserving map onto the lattice of subspaces of FQ to the n, right? So that's kind of nice. Or you still got Creveras complementation. So this is a self-dual poset. But I'm not sure it's the right object. And one reason is that, like, its size is ugly. So Jacques Wang computed these sizes as functions of Q up to about n equals 4, and like they're polynomials in Q, but they're not monic. They don't have positive coefficients. So they're not. It's not like, you know. It should be like, you know, a Q Catalan number or something, right? And it's not. So either this means I don't understand this object well enough, or it means maybe this is not quite the right object, but then there should be something somehow related to it that is the right object. And I don't know what that object is. So that is something that I would be interested if anybody can ever figure out
what. When Q goes to 1, then you get Catalan numbers?
Oh gosh. I really should know the answer to that question. I don't remember. I can find out the answer to that question, but I don't remember off the top of my head. So yeah, so let me stop there.
Are there any questions?
I guess for this poset, you can ask, is it a Cohen-Macaulay poset? What's its Mobius function? And GLN FQ representations on homology?
Yeah.
Probably you're not at that point yet.
So I think that this slide contains everything not depressing that I know about this
Do you know it has like a ill-behaved Mobius function, or you just
No,
you don't know?
no, I do not. I don't know anything about its Mobius function.
Have you found analogs of the matrix tree theorem? Putting weights in reflections, say in the minimal case?
Putting.
For example, you put transvections and local reflections in a different state. You have a nice formula.
So let me say something, and you tell me if it's an answer. In the minimal case, no. I'm just gonna go with no.
Can I start the factorization with any reflection I want?
Can you start the factorization of any reflection that you want?
So is any reflection in this set?
Yeah. No. You can't, actually. Even for n equals 2. One nice thing that happens is if for minimal factorizations, it does not matter what you ask for the determinants to be. So you choose any two determinants whose product is the determinant of the Singer cycle, and we get the same number of factorizations like that. But a consequence of that is that it can't be the same because there are different numbers of transvections and semi-simple reflections. So no, you can't start with anybody. So it's a little uglier in that way.
Have you looked at things like the finite unitary group? Because
So finite unitary group would be.
should it just have to replace all the q's with minus q? But
Yeah.
in theory.
No, not so much. I mean, even say for SLN, it seems a little trickier already, and so.
I think the characters are easier for the unitary.
Okay, all right. I will take your word for that, and I'll think about it. But what we have.
Your math here from that sense W is less than W. Is it also injected?
No.
You restrict it to the because in the non-such fashion that is case.
Yeah, it's not injective. There are. It's a lot bigger. This EC thing is a lot bigger, actually. So I think what I might hope for is say that it was at each rank that was say k to 1 for some k that maybe depends on the rank, and that fails because 35 doesn't divide 240, which is n equals 4, q equals 2 at rank 2. So yeah, no, this is not as nice a map as it could be. So that's one reason maybe to suspect that this is somehow not the right object, and maybe some sub-object of this poset is really better. And we tried a couple of things that failed. So that's why I have this one instead of one of those up here as a proposed object. But yeah, it's not nice in that way, unfortunately.
So you have these various refinements where you fix factorizations with a given number of transactions. Have you considered looking at the sequence of hyperplanes that you get by reading along your factorization through fixed spaces? So given a fixed sequence of hyperplanes, I mean, some are not going to get brought as ever factorizations in the Singer cycle, but do you know which ones are admissible? And if you have the admissible sequence, how many factorizations can you get?
Okay, if you don't fix the order, sorry, if you don't, no. In fact, all sequences of hyperplanes are okay.
Okay.
So what's going on here is you have a lot of reflections for every hyperplane, and so even though not every reflection is okay, every hyperplane has a reflection that's okay. And so I have tried to think about this, and you can get sort of funny things, like you can I was trying to come up with a combinatorial proof of this theorem using that idea, and what I ended up with instead was an algebraic proof that the size of the conjugacy class of the Singer cycle intersect some reverse Broussard or something is, you know, whatever that is, and like that's a nice number, and I really wanted to go the other way. So I can use this to sort of conclude things about what you do if you restrict to particular sets of hyperplanes, but I have not been able to understand that on its own and go back or anything.
Do you have any additional